Okay, today we're going to talk about section 4.7. Section 4.7 is Newton's method. This is a continuation of our journey through the applications of the derivative. What can the derivative do for me? What is there out there that justifies me spending all the time I spent learning this magical thing called the derivative of a function? And today we're going to talk about Newton's method. Now, Newton's method is a bit of an antiquated idea. We all possess a calculator if we have a scientific calculator, especially if we have one that has the computer algebra systems capabilities of some of the higher level calculators. We can find roots of functions today just by simply asking our calculator to solve f of x equals 0. It'll tell us where the roots are. Heck, for most of our calculators, we can graph the function and then ask it to find the intercept between the x-axis and the graph as another way to find the roots of a function. But that was not always the case. And theoretically, there could come a time when we're stuck someplace and we don't have a calculator and we have to find a root. And so we have Newton's method as our approach. So today I'm going to talk about Newton's method. It's going to be a rather short lesson. It doesn't take a lot of time. And I'll do a couple of examples. But it's a calculator-intensive exercise. So when you do the homework in Newton's method, you're going to want a calculator handy. If you have a programmable calculator, something like a TI-89 or an Inspire, that is greatly going to reduce the amount of work you're going to need to compute or calculate the answers to a Newton's method question. If you don't have one of those, you just have your scientific TI-30, well, you can still get the answer, but you may have a blister on the end of your finger by the time you get there. So let's start with Newton's method. Where does Newton's method begin? Well, Newton's method begins here. Y minus y1 equals m times x minus x1. In other words, Newton's method begins with the point-slope formula from algebra. We're going to develop the formula for Newton's method, and while developing the formula for Newton's method, we're going to get to, what we would typically find in a box. Newton's method is, and if we can't remember what's in that box come a midterm or a test, then it's always nice to have an idea of where Newton's method comes from. So Newton's method starts here. Why does it start here? Well, because Newton's method is going to be trying to find x-intercepts, and we can use this equation of a line, right? That's what we have here, the equation of a line. We can use this equation of a line to find an x-intercept. We know for every x-intercept, y is going to be equal to 0, right? That's what we know. So where do we go from here? Well, we're going to turn the point-slope formula into our calculus version of the point-slope formula, right? So what does the calculus version of the point-slope formula look like? Well, it looks like y minus, instead of our y coordinate, we're going to call that f of x sub 1. Y, f of x sub 1, the same thing. Now, we're in a calculus class. We all know slope m is going to be the derivative, f prime of x sub 1, right? We're going to find the derivative at our point, x sub 1. And then we're going to, of course, have x minus x sub 1. So what have we done? We've taken the point-slope formula and we've turned it into the calculus version of the point-slope formula, right? That's what we've done. And this isn't anything that we need to be confused about. Take a second. The slope is the derivative. Of course, the y value is f of x sub 1. Now, from here, we're looking for roots, right? What do we know about a root? I mean, if we draw a quick graph over here, this is a root. And while we don't know the x coordinate of that point, we do know the y coordinate of that point is 0. So if the y coordinate of that point is 0, well, that gives us a hint on where we're going to go from here. Where are we going to go from here? Well, we're going to set y equal to 0. If we do that, what are we left with here? We're left with 0, right? 0 minus f of x sub 1 equals f prime of x sub 1 times x minus x sub 1. Right? All we've done is set y equal to 0. And our justification for that, again, remember, is that we're looking for roots. Roots are x-intercepts. Y always equals 0 at x-intercepts. Y is always 0 there. Now, if we take a look at this equation, this point right here, this is our x-intercept. Right? That's our x-intercept. So if we change that to, well, in our book, they make it x sub 2. So I'm going to go ahead and make it x sub 2. And so I'm going to draw a picture here just in a second that's going to give us an idea. In fact, I'll just do that right now. I'll draw the picture right now. It gives us some kind of justification of where this is going to go. Without the picture, this just becomes a bunch of symbolic manipulation, and I'm not a big fan of symbolic manipulation without some degree of understanding. So here's what Newton noticed when he was looking for roots, and hence the reason we call it Newton's formula, right? Newton noticed this. Newton said, well, if you have some function, right, I'll just draw a function like this, y equals f of x. There's a root, it's right here. We don't know what that root is. That's what Newton said. Newton said we have no idea what the root is. If I know the root, I'm not going to do all of this work to find it. So what was Newton's idea? What was his big idea? Well, what he noticed was, here's the root. He noticed if he just guesses the root, if he just takes a guess, I mean, literally it's a guess. He's going to say, all right, perhaps x sub 1 is the root. Right? That's what he's going to say. He's going to say, well, my root is x sub 1. Well, what do we know if our root is x sub 1? Well, first of all, we can come up here. This gives us a point right here. We know the coordinates of this point. The coordinates of this point are x sub 1, f of x sub 1. Right? Well, that's the coordinates of that point. And Newton noticed something. He said, well, you know, a funny thing, when I plugged this in, I did not get 0, right? This does not equal 0. If it did, I made the best guess in the world. I guessed, and I found the root on my first guess. Well, we didn't find the root on our first guess. So what Newton noticed, right, what Newton noticed is this. If he draws the tangent line to the curve at that point, right, if he draws the tangent line to the curve at that point, that tangent line has an x-intercept. The x-intercept is here. And we're going to call that x sub 2. That's the x-intercept. That's the x sub 2 we found right here. We let y be 0. X is going to be x sub 2. That's going to be our next x-intercept. And what Newton said, well, you know, a funny thing happens. If I take a look at the location of x sub 2 on the x-axis, x sub 2 is actually closer to the root than x sub 1. So if I had to estimate my root, I could use x sub 2 as my estimate, and it's a better estimate than x sub 1. Now, it's not correct. It's not even close to the root. And so Newton said, well, you know, if x sub 2 ended up being closer than x sub 1, maybe if I repeat the process, right, if I repeat the process, we all know what this point is here. This point is x sub 2 f of x sub 2, right? If I repeat the process, and if I draw another tangent line, if I draw another tangent line to this curve at this point, right, I draw a tangent line here, I'll get another x-intercept. This x-intercept I'm going to call x sub 3. And is evident by the graph that we're using here. X sub 3 is closer to the root than x sub 2. X sub 3 is closer to the root than x sub 1. If we repeat this process over and over and over again, Newton said, well, if I keep repeating this process, these x-intercepts are going to converge to this root. My x-intercepts are going to become a better and better estimate of this root each time I draw myself a new tangent line. And that is the process that we call Newton's method. The process says, take a guess, use that guess to build a tangent line. Once you've built that tangent line, find its x-intercept. Not a lot of work. We can all find an x-intercept. We set y equal to 0. That's what we did here. And then draw another tangent line. That gives you a new x-intercept. We'll set y equal to 0, and this will be x sub 2, x sub 2, x sub 2. This turns into x sub 3, and we're going to be able to find x sub 3. And if we repeat this process over and over and over again, each time doing what turns out to be algebra 1 arithmetic, other than the derivative, then we will come up with a satisfying estimate for our root r. So where do we go from here? Well, from here, we do some algebra, right? That was a mistake, wasn't it? So let's just fix that. So we're going to do some algebra. We're going to solve for x sub 2. That's what we're going to do. Now, how do we solve for x sub 2? That's what I want to find. I want to find x sub 2. Now, I set y equal to 0, remember, because this point right here, right, this point right here is x sub 2, 0. That's my justification for letting y be 0. It's not magic math. So how do I solve for x sub 2? Well, I'm going to divide over here. So what am I going to have over here? I'm going to have minus f of x1 divided by f prime of x1, right, equals x sub 2 minus x sub 1. Now we're trying to solve for x sub 2. It's not very hard to figure out how we're going to solve for x sub 2 here. We're going to move the x sub 1 over to this side. And we're going to have x sub 1 minus f of x sub 1 divided by f prime of x sub 1 equals x sub 2. This is the formula that's going to be in the box. This is the formula that is Newton's method. Now, they're not going to write it like this when we write it in the box, right? They're going to generalize this, and what are they going to say? They're going to say the next x that you want to look for is equal to your previous x minus f of that x divided by f prime of that x. That formula right there, this is Newton's method right here. This is Newton's method. So Newton's method is this iterative process. Now, the unfortunate characteristic of Newton's method is that if we want to find the sixth iteration, x sub 6, we need to know x sub 5. And if we want to find x sub 5, I need to know x sub 4. And if I want to find x sub 4, I need x sub 3. And I think you see where we're going here. If someone asks us to find x sub 10, we are going to have to start with x sub 1 and work our way all the way to x sub 10, each time doing this arithmetic. And again, if you have a programmable calculator, you can program this into your TI-89 or your TI-Nspire, and you can do this arithmetic very quickly. If you do not have a programmable calculator, then you're going to be forced to jot down your x sub 2 or your x sub 3 and then plug it into f and make sure you keep enough decimals so your rounding error stays to a minimum, because you're going to compound your error very quickly here with Newton's method if you introduce a rounding error. So this is one of those situations where a programmable calculator turns out to be absolutely essential in terms of minimization of work. Not absolutely essential in terms of solution. Okay? So here's Newton's method. We'll put a box around it. Because, you know, they always have a box around it in the book, so we'll put a box around it. Now, how does one remember Newton's method? Well, I have a hint. I don't think it's much of a hint. I'm not saying it's a miracle hint. But this is what I tell my students. I say, okay, we know that x of n plus 1 is on this side. Nobody ever forgets that. Usually we can remember that x of n is here. And we can remember there's a quotient over here. Where we get confused, right? Where does our confusion come from? Our confusion comes from which one of those turns out to be the derivative. Now, one way to answer that is just to develop it, as we did here. I mean, after all, you're starting with the point-slope formula all the way back up here. In an exam situation, if you're in a panic and you don't know what to do down here, I don't suggest flipping a coin. I don't think that's really the best option here. Flip a coin, maybe you get it right, maybe you get it wrong. This is what I tell my students. I say, well, one option is to reproduce the formula from here. Not usually something that a lot of Calc 1 students like to do, but it does work and it does get us to Newton's method, as it did here in our notes. But I'll give you a shortcut, a simpler idea. This is what I like to tell my students. If you write this down, right? If you write this down, if you take a look at this, there's an F, an open paren, an X, an N, and an open paren. These two phrases, right? I mean, two terms right now are essentially, well, they're not essentially, they are identical. There's 1, 2, 3, 4, 5 symbols up here. 1, 2, 3, 4, 5 symbols down here. Now, what I'm about to tell you, this is not mathematically astute. It's not even logically astute. But hey, if it works on a test, what do we care, right? So this is what I tell my students. What I say is, well, one of these has a prime. If you put a prime on one of them, they're going to have 6 symbols instead of 5. 1, 2, 3, 4, 5. So let's remember that the heavier one sinks to the bottom. Again, I'm not necessarily proud of that. But if it works for you, it works for you. And that's all that matters here. So I tell my students, just remember, the term with the 6 symbols is heavier than the term with the 5 symbols, and therefore it sinks to the bottom. Again, if it works for you, great. If it doesn't work for you, well, start up here and develop Newton's method. It's an option. This one's a little quicker. All right, so how does Newton's method work? And let's start with, first of all, does it always work? And the answer to that is no. Newton's method does not always converge to R. Now I know what you're thinking. Why did you teach me something that doesn't always work? Well, life's full of lessons that don't always work, right? We have to understand the exceptions. So what's one glaring exception, right? One glaring exception that's going to cause Newton's method not to work. Well, remember, x of 1, right? X of 1, this is usually a guess. Now, in the book, on some of the problems, they're going to tell you what to begin with. They're going to say use x of 1 equals 1 or use x of 1 equals 2. And on an exam, we often tell you what to use for x of 1 because we would like your x of 2 to be the same as our x of 2 and your x of 3 to be the same as our x of 3 and et cetera, et cetera, et cetera. So if we pick your initial guess for you, that forces each of your corresponding values of x of n to match our corresponding values of x of n on the examination key. However, on some of the problems, you're free to guess anything you want for x of n. So let's talk about, x of 1. Let's talk about a couple of cases when perhaps you might not make the best choice for x of 1. Well, let's just come over here and take a look at the formula. The derivative's in the denominator. So if f prime of your x of 1 equals 0, then Newton's method fails. So when you're picking your x of 1, if you have that opportunity, don't pick an x of 1 that causes your derivative, right? Don't pick an x of 1 that causes your derivative to be 0 because then you're going to get undefined for x of 2. That's probably not what we were hoping you were going to find. On an exam, on a homework problem, most of the time, we're expecting you to use this to come up with a convergent series, or convergent sequence, of x of n's that converge to R. Now, what does this mean, right? What does this mean? Well, we know what this means from a previous lesson. We know that that means you had the audacity or the luck, whichever way you want to look at this. You picked x of 1 to be local max, or you picked x of 1 to be a local min. Because if you do that, then x of 1 is going to be 0. Now, it almost goes without saying, but because this is a lesson, it doesn't go without saying, it's going to be said. If you choose an x of 1 where the derivative is undefined, obviously this is not going to work. This is not going to work. So that's another case. I feel like I don't even have to write that one down. Now, what is another opportunity for Newton's method to let us down, right? What would be yet another opportunity for us to be working on Newton's method and Newton's method says, oh, I'm sorry, I'm not working for you right now. Well, another place where Newton's method could fail for you is if your function has more than one root and you're looking for this root. And even if it doesn't have more than one root, but if you're looking for a root and your function has a max or a min, and you pick your initial guess to be on the other side of the max or min, what we would call, in this case, the wrong side. My root is on the left-hand side of my max here, but I've picked my initial guess on the right-hand side of my max. This series of tangent lines, well, in this case, of course, this series of tangent lines would find is this root, but if there wasn't a root over here, this series of tangent lines wouldn't find us any solution. How do I know that I've done that without graphing the function itself? Well, you start finding x of 1, which usually is just a guess, and then you calculate x of 2, and x of 3, and x of 4, and x of 5, and x of 6. We all know what convergence means. We know that's getting closer and closer and closer and closer to a number. And in this case, if you pick your initial guess on the wrong side of a min or a max, you're not going to have any type of convergence. Your x sub n's are just going to be bouncing back and forth. They're going to not be convergent. And you're going to look at them, and by the time you get to x of 4, x of 5, you're going to start to think to yourself, perhaps I've done something wrong. Now, more than likely, it's not that you've done the arithmetic wrong, because, of course, we all have a fail-safe way of remembering where to put that f prime. In that case, you just want to go back. You don't need to draw the graph of the function. You don't need to use all those techniques that you were taught earlier to find mins and maxes. Just make another guess. Right? Just make a different guess. Move away from your initial guess and see if in that case we start to get an answer. This is an applied portion of the calculus book, right? So in the world of applied, we just pick another guess. Try something different. Don't overanalyze. Don't be a pure mathematician and start trying to find mins and maxes, and just guess again. It's simple, it's quick, and relatively painless. All right. So what am I going to do now? Well, I'm going to work out an example of Newton's method. Now, because I don't want to sit here and bang away on a TI-89, and this video is not how to use a TI-89 or a TI-Nspire, I'm going to cheat. I'm going to tell you that right now, and I'm going to do the example that's in the book. Why? Well, because all the calculations are already there, and we don't have to spend all the time necessary working out all the mundane calculations, right? Let me just erase all of this. We'll leave Newton's method right here in the box, and we'll work around that with our example. All right, so I'm not a big fan of doing examples in the textbook. I often think that you have the opportunity at your age to be able to read a textbook, and why should I do examples that you could actually read yourselves? But in this case, because of the nature of the problem that we're working with, I am just going to quote-unquote cheat, and I'm going to do the example that's in the book. Now, to give you an idea of how complicated Newton's method is, right, there are only 3 examples in the book that I happen to teach out of, and so if there's only 3 examples, it can't be that bad, right? We all know, having been through a lot of math classes to get this far, that when we're doing the reading, and we all religiously read the book, we all do that. Nobody just depends on the instructor's lecture to learn calculus. I mean, the book is our constant companion, he says with a large amount of sarcasm. But when we at least look at the book, if we look at the book and there's 22 examples, well, we start to have a little bit of a panic attack, and we realize, whoa, there is a lot going on in this section. But the converse of that is when we look at the book and we see 3 examples, we're like, hey, I think I'm going to enjoy this homework. So let's do a Newton's method problem. What do we have, right? This is a typical Newton's method question. They give us a function. In this case, I'm sorry, they give us an equation because we're looking for roots. So we have x cubed minus 2x minus 5 equals 0. And all of us know, if we have a programmable calculator, we could type that in, it would tell us the roots, and we would be done. And we all know that because this is a third degree polynomial, we're either going to have 3 real roots, or we're going to have 1 real root and 2 complex roots. Those are our only options. We remember that from pre-calc. But today is a day where we're playing the game that we don't have a calculator that will solve this. Hey, does anybody want to get that?
Call from 213.
Oh, we'll never know who that was from. The great mystery of all time. So, back to our problem. We have x cubed minus 2x minus 5 equals 0. We want to find a root to this, right? And again, we're not sure if it has 1, if it has 2. Well, no, it doesn't have 2. If it has 1 real root or 3 real roots. So the way the problem reads, it says start with x of 1 equals 2. And it says find x of 3. Okay? Find x of 3. So how are we going to go about that? Well, we're going to use Newton's method. Now, to make Newton's method easier, what do we need? Well, we need to know the derivative of our function, right? This right here is our f of x. So I like to do that off to the side, right? I rewrite my f of x. I have x cubed minus 2x minus 5. Now, it's always imperative that we actually copy the function correctly. We've all done that on a test. So f prime of x is going to be what? This is going to be 3x squared minus 2, isn't it? We take the derivative of that, we get 3x squared minus 2. Now, they want us to find x of 2 using x of 1 equals 2. Right? So we're going to calculate x of 2. And from our formula down here, what do we know x of 2 is equal to? It's equal to x of 1 minus f of x of 1 divided by, the heavier one sinks to the bottom, so that's f prime of x of 1. So what do I need? Well, I need to go find myself f of x of 1, and I need to find myself f prime of x of 1. So we can do that work over here, right? We can do that work over here. So what is f of x of 1? Well, f of x of 1 is really f of 2, right? They told us to start with 2. And again, on some of the problems, they're not going to give you x of 1. So you just pick one. Pick something that's easy to plug in. Now, where do we go from here? Well, 2 cubed is 8. Minus 2 times 2 is minus 4, minus 5, and we get negative 1 for f of 2. And then we've got to find f prime of x of 1. That's going to be f prime of 2. And so what do we get when we plug in 2 here? We get 2 squared is 4. 4 times 3 is 12, right? So we get 12 minus 2, so we get 10. Right? So those are our 2 values. So where do we move? Well, we just plug them in. That's what we do. So what is this going to be? This is going to be 2 minus f of x of 1 we said was negative 1. We'll go ahead and put that up here like this. And then f prime of x of 1 is 10. So this turns out to be 2.1. Right? 2.1. So that's our first value. So that's x of 2. Now we know 2.1 is not a root of this. Newton's method doesn't converge that quickly. It is shocking, to be honest with you, how quickly Newton's method does converge. And if you're wondering how your calculator finds roots, to be honest with you, it uses Newton's method with a couple of adaptations thrown in for all those number theory people out there. And then we can actually say that when Texas Instruments programs your TI-89 to find roots, this is what it does, because Newton's method converges very quickly, very quickly. So they asked us to find x of 3. So we have one more step. Right? This is where our calculator is going to come in really handy, because now what do we have? We have 2.1 minus, and this is going to be f of 2.1 divided by f prime, that again sinks to the bottom. And so what are we going to be asked to do? Well, we're going to be asked to find, right? We're going to be asked to find, over here, we're going to have to find f of x of 2, which is f of 2.1. And then we're going to have to find f prime of x of 2, which is f prime of 2.1. Now, I'm not even going to begin to act like I'm going to calculate those. I'm just going to copy those. Well, I was going to copy them out of the book, but when I take a glance over here at my book, what I see is they didn't individually calculate this number or this number in the example I'm working with. So we're going to write out what they wrote out in the book. And so that is absolutely incorrect. There we go. So we're just going to copy what they have here and then wave our magic wand and come up with an answer. So what do we need? We're finding f of 2.1. F is this function right here. So what do we have here, right? We're going to subtract a fraction. So we're going to have 2.1 cubed minus 2 times 2.1 minus 5, right? That's going to be our numerator. Our denominator is going to be 3 times 2.1 cubed minus 2, right? And through the magic of copying things out of the textbook instead of calculating them ourselves, I can tell you that this turns out to be 2.0946. And that's approximately 2.0946 because in the book they've rounded it to 4 decimals. All right? So this is one example of a classic Newton's method problem. I'm going to do one more example just so we can see another application of Newton's method. To be honest with you, students often think this is a totally different kind of problem. When they're looking at their homework, they're like, wait, where did these problems come from? How am I supposed to do this? So I'm going to work out another example. It's again Newton's method, but it looks a little different. And you and I, we will try to discuss how the appearance of it being different is really nothing more than that. Just the appearance of it being different. It's really the same problem. Okay? So where do we go from here? Let's see what can another Newton's method problem look like. Well, there's problems that start like this, rather innocuous looking problems. It says, what's the 6th root of 2? And again, if we have a calculator, we take 2, we raise it to the 1/6, we're done. But, it could be the case that our calculator decided today was the day to have the batteries die, and we don't have batteries. So what can we do to estimate the 6th root of 2? Well, as it turns out, Newton's method will do this for us. So how would one use Newton's method to estimate this? Well, we need an equation, right? Newton's method says I'm going to find zeros, roots, x-intercepts of an equation. So what do? We have to start pulling this apart, right? We have to ask ourselves, what is this the solution of? We'll end the sentence in a preposition because it's a math class. So, actually, it's a question, isn't it? See, double math. What is this the solution of? Well, it doesn't take a lot of thinking for us to realize that this is the answer when we've taken the 6th root of 2. I mean, that's literally what it says. So, if I had x to the 6th, numbers, they're hard. If I had x to the 6th equals 2, the solution to this would be to take the 6th root of both sides, and I'd have x equals the 6th root of 2. And so I'm looking for zeros. I need a 0 on this side to look for zeros, to look for x-intercepts. So the equation that we're trying to operate with here is this. X to the 6th minus 2 equals 0. So that's the first step when they give us a problem like this and ask us to use Newton's method to estimate that. We need to know, right? We need to know what my function is. So this is going to be my f of x. Now, off to the side, we know f of x is x to the 6th minus 2. We know the derivative of that, of course, is going to be 6x to the 5th. Now, if we just put that into Newton's method, right? If we just put that into Newton's method, we can get a generalization for Newton's method. We can say that the n plus first iteration is going to be equal to the nth iteration minus, and f of x goes on the top, so we'll put a fraction bar. So that's going to be our nth value raised to the 6th minus 2 divided by 6, I'm putting the derivative in here, times the nth value raised to the 5th. That would be our adaptation of Newton's method giving this problem. Now, where do we go from here? Well, we need to guess, right? In this case, we were not given an x of 1, so we'll guess x of 1 equals 1. We'll guess that the 6th root of 2 is 1. Now, we know that's not true. 1 to the 6th is not equal to 2. 1 to the 6th equals 1. So we know that's not a solution. Now, this is where having a programmable calculator comes into play and makes this problem very simple, because what would we do then? Well, we would program this equation right here, well, this side of the equation into our programmable calculator, and then we would ask it to calculate that when we plug in a 1, then we would store the answer, right? Now, I can tell you that x of 2, and again, I'm just copying this out of the book, because I'm not going to do the arithmetic here. X of 2 turns out to be approximately 1.166666667 if we round it to 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. Obviously, the answer is 1.1666666 repeating, but if we round it to 9 decimal places, this is approximately x of 2. Now, again, if we had a programmable calculator, we could then just push the, programmable calculators have a button where you hit second something, and the answer becomes your input, and we could input that number into here, kick out an x of 3, input x of 3 into here, kick out an x of 4. Now, what did they ask, right? What did they ask? And I didn't really write that down up here. What they asked is they want 8 decimal place accuracy. Now, if you do not have a programmable calculator, then we are going to be sitting here punching away on TI-30 for quite a while. Your TI-30 will store this. Hopefully you know how. If you don't know how, Google that would save you a lot of time. It'll store answers, but the problem with your TI-30 is you can't program this equation back into your TI-30. Now, what does 8 decimal place accuracy look like? Well, let's write down x of 3, right? We'll use another symbol for approximates. So we get 1, 2, 6, 4, 4, 3, 6, 8. Now, if we take a look at this, if we take a look at x of 3 versus x of 2, right? They match in the first decimal place. So we would say that x of 3 has 1 decimal place accuracy because it matches x of 2 in its first decimal place. So when they want us to find 8 decimal place accuracy, I was just trying to figure out if I spelled accuracy right. So, and if it's not, well, stop the video now and never watch another one, or forgive me. Those are your two choices. So, right now we have 1 decimal place accuracy. When we do x of 4, right, and again, I'm just copying this down in the book, x of 4 turns out to be 1.1224977. And now if we look, we're up to 2 decimal place accuracy. And we would just keep repeating this until we match on the next answer. It matches all 8, because they want 8, all 8 decimals on our previous answer. All right? And as it turns out, taking a gander at the book over here, we get there in x sub 6. X sub 6. That's what I meant earlier in the video when I said how quickly Newton's method converges. It only took 6 iterations of Newton's method to get to 8 decimal place accuracy. And unless we're, actually grinding the mirror for the Hubble Space Telescope, there aren't a lot of things in the real world where we need 8 decimal place accuracy. When we're building the cabinets for your kitchen, we're not trying to get those cabinets built to 8 decimal place accuracy. All right, so that'll conclude my lesson on Newton's method. That leaves us 4.8 from chapter 4, and then we're done with chapter 4. And then 5 sections to go for those of you that are in my Cal State class. 5 sections to go, and semester's over. All right, I hope everybody's having a good day. Thank you for your time.